Hello everyone, my name is Dainus Yankus. In today's presentation I will cover the work I did during my placement for the past year working as a research assistant on energy-aware runtime management of distributed many-core web server systems. I work in Microsystems Research Group in the School of Engineering at Newcastle University, and my supervisors are Rishad Shafiq and Alex Yakovlev. Now let's talk about the project aim and objectives. So the key aim of the project was to develop energy-aware runtime management for distributed many-core server systems. To achieve this, I started by exploring existing runtime management methods and setting up a server as well as selected web application for a case study. Then I did characterization experiments, which included a lot of profiling in order to understand if I can model the behavior of my application and use it when developing resource management approach. After gathering enough experimental data, I simulated the behavior of my application in order to test the developed resource management method. And lastly, the most difficult part was to integrate the developed approach into the runtime and evaluate it in a real web server environment. The purpose of energy-aware runtime management is to allocate system resources in a way that it can achieve energy-efficient operation while maintaining acceptable service of quality. Typically, the existing methods often limit the resource management granularity by only scaling the number of active servers. Therefore, there is an opportunity of introducing a fine-grained resource management that can offer more elastic control of resources under dynamic workloads and provide better energy-saving opportunities. The management of distributed server resources also comes with the challenges. To start with, it requires a coordinated runtime controls across available servers. Also, the design of runtime can depend on systems modeling, which is limited by the lack of workloads to exercise the system in web server environment. Due to the nature of dynamic workloads, the profiling required for modeling is time-consuming and impractical for covering multiple workload cases. And finally, the evaluation of the design technique requires a real web server environment for testing. Now I'm going to discuss the system's architecture used in this work. Firstly, let's have a look at the system's block diagram. We have a web server cluster which consists of 4 Odroid XU4 platforms connected through a network switch. The server cluster hosts a WordPress blog site cloned across available servers. The monitor is responsible for providing performance and workload metrics which are required to guide runtime control actions. The load balancer equally distributes the incoming web traffic across active servers. Workload generator was developed to apply different web workload patterns which are required for profiling and testing systems performance. And at the core of runtime management is horizontal and vertical scaling approaches which act as control knobs, allowing to allocate resources in order to minimize energy consumption while maintaining a desired performance of web application. These will be discussed more in the following slides. And lastly, the workload generator, monitor, load balancer, and the runtime management logic are deployed on a separate machine from a web server cluster. Hierarchical resource management uses two control knobs to scale available resources of the server cluster. Vertical scaling allows a fine-grained control of individual server resources through dynamic voltage and frequency scaling. It helps to adapt to smaller workload fluctuations and sustain energy-efficient operation by selecting optimal operating points for given performance requirements, while the horizontal scaling enables to take control of resources by managing the number of active servers, and is applied when the vertical scaling can no longer sustain desired system's performance. The selection of vertical scaling actions is based on reinforcement learning approach called QLearning. The scaling decisions are learned through the agent's interaction with web applications environment. If we take a look at the diagram on the right, the QLearning agent chooses and applies an action to the server cluster. After some time, the system's response is observed through the monitor. In this case, it is a web service response time and the new state. Also, the reward is estimated after taking action at a given state. The decision to choose an action in a particular state is presented by policy. The policies are estimated using QLearning algorithm and stored as Q values in a Q table. An example of Q table is shown on the right. It can be seen that the best action for a particular state is presented by the highest Q value. Now, if we take a look at the equation, the first component is a Q value of current state action pair. The second part of equation is a learning rate multiplied by so-called temporal difference of current and new state. A learning rate allows to control how quickly the newly estimated Q values replace the old ones. The reward is specifically estimated to reflect how the taken action affected the application's performance with regards to quality of service requirement. The best Q value of a new state is multiplied by discount factor, which determines whether to give more weight to current reward or long-term future rewards. To better understand how vertical scaling works, let's have a look at the QLearning process shown in the diagram on the right. So initially we start by observing current state of the system. In this case, the state is a number of connected users sending a request to the web server. Then the agent has to choose and apply vertical scaling action at a given state. So the scaling action is defined as a global voltage frequency configuration of CPU cores across active servers. Then after this action is applied, the system response is observed. Depending on the workload or application, it may take seconds or up to a minute for the taken action to be reflected in the system's response. A new state is then observed and the reward is estimated using the find function, which gives negative rewards for actions resulting in quality of service violations, while positive rewards are given to actions leading to the system's performance close to desired quality of service requirement. And lastly, the policy is updated using Q value learning algorithm, and a new Q value is stored in the Q table. So this process is repeated multiple times until the agent learns the best actions for given states. The learning process can be divided in two phases called exploration and exploitation. Exploration helps to learn new policies in unexplored environments by taking random actions, while exploitation allows to maximize the rewards by selecting the best actions from already learned policies. So the challenge in reinforcement learning is balancing these phases to allow enough learning to avoid taking suboptimal actions due to the lack of exploration, but maximizing long-term rewards by taking already learned optimal actions. So the transition from exploration to exploitation is achieved using exponential probabilities, which decay with explored actions at a given state, as shown in the figure below. In addition to discussed vertical scaling method, the horizontal scaling is used to manage the resources by gradually increasing or decreasing active servers in response to varying workloads. The scaling decisions are made using a set of rules and can be described by two actions, scale down and scale up. The scale up action is taken in order to react to increased workload intensity, given that vertical scaling cannot longer improve the performance to meet the required quality of service. The scale down reduces the number of servers as workload intensity decays in order to increase resource utilization of the cluster and save energy. Optimal scale down actions for a given number of servers are learned at runtime. A history of scale up decisions are stored in the horizontal scaling table, and with enough scaling decisions, a minimum scale down state is found that ensures that remaining resources can maintain quality of service after scaling down and avoid instability caused by alternating scaling decisions. Initial testing of design management approach was achieved by simulating web application performance of two servers. The workload was applied varying number of users with a fixed request rate. After applying the workload, the QLearning agent started to explore by taking random vertical scaling actions. The scaling actions were limited to 3 frequencies of A15 cores, which include 0.8, 1.4 and 2 GHz, while A7 little cores were set to maximum frequency. The agent took multiple actions at the start of exploration, and it can be seen that some of them resulted in quality of service violation. As the workload pattern was repeated, the agent started to exploit learned actions. In this case, the number of quality of service violations was significantly decreased. Then more intense workload was applied, which triggered horizontal scaling actions by enabling the second server. As before, the agent started exploring new states by taking random actions. As the workload intensity decayed, the second server was disabled. The learned actions were exploited, resulting in minimum violations in quality of service when the workload pattern was repeated for the second time. Therefore, this experiment shows the system's ability to learn vertical and horizontal scaling actions at runtime. The developed runtime management technique was integrated into web server environment. The exploration process with two servers is shown in the figure on the left. It can be seen that the agent took multiple scaling actions during exploration, and as expected, some of them led to multiple violations in quality of service. The figure on the right shows system's performance after 2 hours of exploration. In this case, the agent started exploiting already learned actions, and as expected, the number of violations were reduced significantly. Therefore, the results of this experiment indicate the successful runtime integration of proposed management technique into web server's environment. In this experiment, I've transferred the vertical scaling actions from a single server queue table to a 3-server cluster. Assuming linearly scaled out performance when adding servers to the cluster, the queue values were transferred by normalizing the unexplored state by a number of servers, then finding the closest state in single server's queue table for transferring state action pairs. For example, if we have 2 servers running it with 20 users, the queue values corresponding to 10 users would be transferred from single server's queue table. The results in the figure on the right indicate that 3-server cluster was able to maintain stable performance with minimal quality of service violations when the workload was applied. Also, the size of queue table could be reduced by identifying states with similar action policies and grouping them into larger classes. The power consumption of proposed resource management method was initially compared against well-known Linux runtime governors, performance and on-demand. To do that, a fixed workload pattern was applied to a cluster of 3 servers to test each method. The proposed resource management technique outperformed on-demand and performance governors by 10 and 20% respectively. As expected, the on-demand governor performed better than the performance governor as it dynamically scales frequency in response to CPU load. To summarize, the energy-aware runtime management of distributed many core web server application using QLearning was presented. The aim and objectives were successfully met, and the results of runtime performance in web servers environment showed that the proposed resource management was able to learn and apply optimal scaling decisions under varying workload patterns with minimal quality of service violations. The scalability of the proposed method was demonstrated by transferring vertical scaling decisions from single to 3 server cluster configuration. The comparison against Linux governors showed that the management method was able to reduce power consumption while achieving required quality of service. Thank you for watching.